doesn't matter which distance you are, it rises relative to eye level. That means due to perspective and convergence, no matter your elevation, you'll always have the horizon relative to your field of view. Therefore, not physically dropping down, optically rising as perspective dictates.
So this is Debatism X on the Jeranism channel, and he's hosting MC Toon and Fight the Flat Earth versus Sovereign Soul and Flatzoid. And what you just heard was Flatzoid trying to teach MC Toon perspective in real time, trying to teach him how a horizon works. So I'm making a small series on how the horizon works in reality or on a flat earth, take your pick.
All right, could you show measurements and of course not calculations, measurements that you have done or somebody's done of the horizon rising to eye level at some high elevation, please?
So ask and you shall receive. Here is a measurement, MC Toon, of a horizon at eye level at 180,000 feet. So you heard Flatzoid tell you that the horizon rises relative to eye level, and he is absolutely right. And flat earthers who claim that the horizon rises to eye level are not wrong, but there are a couple distinctions to be made. For starters, it is perspective that causes the horizon in the first place. Go down low to a flat surface, and you will see that there will be a horizon. And we don't claim that the horizon rises to zoomed in eye level. When you zoom in, you spread the gap. So at 3 miles distance, the gap between a 6-foot observer and the horizon is indistinguishable. This is what causes the horizon in the first place. But with instrumentation and zoom lenses, you can measure a small drop when you zoom in. So I'm going to give examples of this to explain exactly what I'm talking about. And last but not least, the horizon is a function of distance. So on a crystal clear day, even fully zoomed, the horizon will be at eye level. But when it's foggy and hazy, especially like the pictures you showed from your airplane where it's hazy and you can't see very far, the horizon will have a slight dip in it with instrumentation, not with the unaided eye. So this is what we're taught in art class. You draw a straight line across a piece of paper to represent the horizon, and then a point to represent the vanishing point. Okay, it has nothing to do with Earth curve. We're all told that perspective is just things getting smaller in the distance, which is true, but there's a key component being left out. Okay, when it comes to the horizon or the critical angle, you can't zoom in on the horizon and you're not changing the angle. So picture a checkerboard. Picture a bunch of them lined up. You could get down low to it and you're going to eventually lose the angle to distinguish the checkers. And where they all combine is your horizon. Okay? Zooming in won't change that angle. So it will not change the horizon. It's going to rise up to eye level and no more and no less. Now, when you zoom in, like I said, you could spread the gap. If you wanted to measure a drop, you could zoom in far enough and measure your exact height. For example, let's say we have a 4-foot observer height above this railroad track. Okay, would anybody claim that this horizon is formed because of Earth curve or because of the limit of our vision? So we're going to draw in a horizon. Now, the 4 foot between the railroad tracks and the observer height is no longer distinguishable. Now, if we zoomed in far enough, we could measure the exact 4-foot gap. Okay, in turn lowering the horizon by zooming in, but we're not going to change that angle. Therefore, the cross ties that have become jumbled together because of the critical angle, zooming in is not going to change that. We're not changing the angle. Therefore, we're not changing the horizon. This might help Globers understand better. Okay, so let's say we have Jane on the beach and she's looking through an auto level at a 6 foot above sea level height. Okay, in front of her is the 6 foot and 6 foot all the way into the distance. But with the unaided eye, you see that the gap between her 6-foot observer height and the water or the horizon is 0. There's no distinguishable gap. Now zoom in or use instrumentation and you can measure a teeny little gap. Okay, so that's why we've had to change our argument, saying that the horizon rises relative to eye level. The two other determining factors which dictate the position of the horizon is refraction and visibility, which I will cover thoroughly in part 2. So I want to thank everybody for watching this all the way to the end. If you enjoyed it, give me a thumbs up and be sure to subscribe if you don't want to miss part 2.